Hello, this is Jeff Scott of Rankin Technical College, and right now I'll be coming at you with the first of probably at least 16 lectures for the Java programming class. And our textbook, as you can see on the screen right now, is starting out with Java Early Objects, 5th edition by Tony Gaddis. And Chapter 1, which I'm going to go through right now, is an introduction to computers and programming. Now, there's a lot of good material in here, but there's a lot of material that I probably won't cover because either A, you'll get it in another class, or B, it's not exactly that relevant. But I do want to talk a little bit about programming and about a few of the other things in here. Okay, so as we go on, we can see we have here the following main topics. After the introduction, why program to begin with? All right. Then we discuss the difference between hardware and software, a little bit of talk on programming languages, what is a program made of, the programming process, and object-oriented programming. So, as mentioned, this book teaches you how to use Java. Java is an excellent programming language for a lot of reasons. One is it's meant to run on any computer that has access to what's called the Java Virtual Machine, or the JVM, which pretty much is most every computer that's been sold in the last 10, 12, or more years. All right, you can use Java to create either full-fledged applications, like for a payroll system, for example, or you can use it to write applets, which run under a browser. This chapter, as mentioned, will review some hardware and software fundamentals and give you a generic kind of general look at programming. All right. Now, the big thing to realize when you start looking right here, and no, it's not on this slide, but what I want you to understand is basically there's two different types of programs that people write. One are programs for what are typically referred to as system software. Could be an operating system or some kind of a utility or helper program that helps with the computer. We're not concerned with those kind of applications in here. Instead, we are going to be concerned with application programming. And, we're going to write fairly simplistic programs in here, but they'll get a little bit more complex as we go on. All right? All right. Computers, as mentioned, can be used for a lot of things. Some of them are shown right there. They're versatile computers because they can be programmed, and programmers write the programs. That should make sense. So, why program? Could give you the smart aleck answer and say, well, you program because if you want to pass this class, you have to learn to program. But when you program, these are the things, or among the things, that you have to learn. The logical flow of programming instructions, mathematical procedures. And I've had many students tell me in the past, well, I can't do this because I don't do math. The amount of math you should have to do in this class is minimal. And again, it's you're telling the computer how to do the math, much like when you type something into a calculator, you're telling the calculator to do the math. The layout of programming statements, what actually appears on the screen, all right, the way information is presented to the user, the program's user friendliness. In other words, if you create this terrific application for other people to use, but it's so hard to understand that no one uses it, what have you actually accomplished? And all sorts of forms of documentation. All right. Now, the key thing in I think at least on this slide is the second bullet. Programs rarely work the first time they are programmed. So get used to making mistakes. And actually making mistakes is a good thing because that's how you discover, all right, flaws in your program, flaws in your logic, etc. As it says here, programmers must perform the following on a continual basis: analyze, experiment, correct, and if or as necessary, redesign. Now the last bullet in here talks about syntax. And syntax are the rules of the language. If you were to look at your book right now, you'd notice that your book is made up of a series of chapters. Every one of those chapters is made up of a series of pages. Every page is made up of a series of paragraphs. Every paragraph is made up of a series of words, actually of sentences. Every sentence is made up of a series of words. Every word is made up of a series of characters. So you can see, there's a certain syntax or certain types of rules that you are expected to follow as a programmer. Now that should just really, and truly, hopefully at least, that just makes sense to you. If I was going to walk into class today and say, good morning, everyone, I'll be your instructor, my name is Jeff Scott. Well, it would sound a lot different if I walked in and said, Scott, morning, will instructor be good Jeff, something like that. It doesn't make any sense. So there's a certain type of rules that you follow. All right, so to talk a little bit, and that's all it's going to be, is a little bit about hardware here. Hardware are the physical components of a computer. You can touch hardware. The major components of a computer are the CPU, or central processing unit, and most people don't realize, but typically the size of a CPU in a computer is about the size of a postage stamp. The main memory of the computer, which is also known as its RAM, or random access memory. Secondary storage devices, flash drive, etc. And input and output devices. For most of the class in here, there will be, what I'm about to tell you, there will be exceptions. But for most of the class in here, your input will be done using the keyboard or the mouse, and your output will typically be shown on screen. So here's a picture of some of the hardware. So the CPU is kind of the brain of the computer. Again, I don't want to read this to you. You can see what it is. The CPU consists of the control unit and the arithmetic and logic unit. The ALU, as mentioned there, performs all of the computer's mathematical operations. The control unit is kind of like a conductor. It coordinates all the operations of the computer. The whole idea of running through a computer system is, what a computer is supposed to do is take inputs, all right, which typically are called data, known as data, and produce outputs, which are typically known as information. The data may or may not make sense depending on who's looking at it. For instance, if I walk into a bank and I see the personal banker there, and she or he, let's even say a bank teller, and she or he has been putting in a bunch of, I don't even know if they do it this way anymore or not, but let's say that they're putting in a bunch of deposits that have gone into the system. And they type in a series of 30 or 40 numbers. Now that might make total sense to the person keying in the numbers, but to me it's just a bunch of random numbers that don't mean anything. The CPU, as mentioned, performs this 3-step process to process or convert data into information. It fetches, so in other words, it goes into main memory and it grabs the next sequence. It decodes, so it has to put it in a way that the computer can understand it, and then it executes it. In other words, it tries to do what it was told to do. Main memory, I already mentioned, is called RAM. The key thing with main memory, and it's not even shown on here, is RAM is subject to electronic current. So in other words, I can write the best program in the world, I can run it, but if I don't save my output in some way, as soon as I either get out of the program or close the program down or whatever, that output is gone. RAM, as mentioned, is typically divided into units that are called bytes. All right, and a byte is actually kind of an acronym. It stands for a binary digit, so it's 8 bits that can be either on or off. On signified by a 1, off signified by a 0. Each of these 8 sets of bits represents a character or a number. Now, please take a look at that third bullet here. Each byte in memory is assigned a unique number known as an address. In much the same way, each student at Rankin Technical College is given a couple different things. You're all given some kind of an ID number, and you're all given your own unique Rankin email address. Okay? I already mentioned to you that RAM is volatile, meaning it's subject to electronic current, so there's nothing new there. And RAM is typically looked at as a series of bytes, all right, with their addresses. Now, I do want you to realize when you take a look at the picture here, I'm not going to sit and fight with the author on this, but they mentioned that the number 149 is stored in the byte at address 16. That might be true. But what is stored there is not the number 149 like you see. It's a series of ones and zeros that mean 149. All right? Same thing with the other ones shown there. Secondary storage, and I mentioned flash drives. The computer that I'm using, the laptop, does have a CD drive in it. Disk drives are very rare that you see one anymore. All right, and there's some other examples here too. What secondary storage provides you that primary storage does not is secondary storage provides you with the ability to save information so that when the computer is turned off or loses power for whatever reason, the information is still there. So in other words, it's non-volatile storage, also known as persistent storage. The common input devices, I've already mentioned most of these to you, the keyboard, the mouse. All right. Common output devices, typically a monitor, could be a printer. And as you'll see in later chapters, another input way that you can input is by using what's called a file, and you can also output to a file. So we'll take a look at both using a file for input and for output later on in the course. All right, already mentioned there's 2 different kinds of software, typically referred to as operating systems or system software and application software. An operating system, and I don't even know if I can do this on here or not, but let's try it anyway for the heck of it. Let's see. I've done this before. I don't know if this is a great idea or not a great idea, but I'm going to try it anyway. So I'm going to come over here. And I'm going to draw this kind of big circle right there. Move it over. And I want it to look pretty circular if I can. That's not perfect, but that's not bad, this blue one here. All right. In fact, we'll put the color like that. Now I'm going to come in and I'm going to do this again. You'll see why in just a minute, hopefully. But I'm going to put another circle inside of here. All right, and then finally I'm going to create one more circle. And that one I'll make kind of a reddish or orange, whatever. All right, why am I doing this? Because what I want to show you is this. If you can imagine, go back to my shapes here. If you can imagine that this innermost circle, the one right there, that's the computer, also known as the machine. And if you can imagine that right here, that's the user. So you've got on the inside, you've got the computer. On the outside, you've got the user. Well, in between those two, you have the operating system. That's what I'm trying to show you. The operating system is sometimes referred to as the person-machine interface. There's the machine, there's the user. So the machine is there in kind of brown, or whatever you'd call that. The user is there in kind of a mustard type of color, and the operating system is between those two. So the operating system provides the person-machine interface, or it's sort of the buffer between the user and the machine itself. Now, they give you more on here that I didn't say, and it's totally fine. As they say, I agree. The operating system manages the computer's hardware devices and controls the processes. And the rest of the stuff that's in here is all true also. I agree with all of it. Most popular operating systems are typically today Windows, all right, Mac OS, and Linux. And Linux is just the free version of Unix. Already mentioned what application software is. If you kind of look at it this way, that although all of us use an operating system on our computer, all right, we typically, most individuals don't program things using the operating system. And all they use the operating system for is, as mentioned before, it's just the interface between the user and the machine. All right. On the other hand, application programs or application software is software that's so useful to the user. It's like I'm using PowerPoint right now, which is an example of application software. Word is an example. And there are plenty of other ones. So what's a program? A program is a set of instructions the computer follows to perform a task. That set of instructions are typically known as an algorithm. Now, some books will also call it a recipe. And the idea is if you put 10 cooks in a room and each cook creates the same recipe or creates the same dish using the same recipe and doesn't deviate at all from what's on the actual recipe, all 10 should look and taste the same. Now, we know that probably in life it doesn't normally work like that, but that's the idea. So a programming language is the language used to write computer programs. The one we use again in this class will be Java. A program is a set of instructions that allow the computer to solve or perform a task. Could be many tasks. I already mentioned that an algorithm is a set of defined steps for performing a task or solving a problem. All right, when we first start out, the steps in the algorithm will be performed sequentially. Later on, we'll talk about how you can change that. Remember, the only thing the computer can understand are zeros and ones. So as we write code in a very English-like language, the system has to take what we've written and convert it into a series of zeros and ones. This is an example right here. Now, back in the olden days, I'd say back in the, I don't even know when it would be, the 70s. All right, so we're talking 40 years ago. Machine language, which are these zeros and ones, are the way that virtually everyone programmed. After machine language, we went to what's called assembler, which is still used today, and it's sort of a cross between a modern-day programming language and machine language. All right, but today you've got more high-level languages. As it says, they use words instead of numbers. They're more English-like. But the program, as it says, that you write in a programming language must still be translated into machine language somewhere along the line. Now, in your book, you see this table, and the table has many of the better-known programming languages. All right? In the program here at Rankin Technical College, you learn C#, you learn Java, you learn JavaScript. All right? Now, me, myself, and I'm not saying this to be a braggart or anything like that, I used to teach BASIC. The first true language, I did take an assembler class, but we only wrote one program in there. But the first true language that I learned was Fortran, which is very much a mathematical language. All right. I used to teach COBOL when I got into teaching, which seems like many, many, many a year ago. All right. We're talking in the late 80s to begin with. I taught COBOL, the Common Business Oriented Language. I've also taught Pascal. When I got my 2-year degree and went into the workforce, I was a C programmer. I've taught C++. I know C++. I'm actually currently writing a book on C++. C# is the language that you've already learned. Java is the language we learn in here. So let's take a look at what that says. Java is an object-oriented language invented at Sun Microsystem and now owned by Oracle. It may be used to develop standalone applications that operate on a single computer. All right. Applications that run over the internet from a web server, and applets that run inside of a browser. Okay, so we'll look at most of that stuff. You've already had JavaScript. Perl is another well-known language. All right. Taught a Perl class, but it was probably 15 years ago. PHP is another server-side scripting language. All right, very popular. Python is a fairly new language. It's another object-oriented language. Ruby is another language that's typically used to develop web applications. And Visual Basic, in many ways, Visual Basic is very similar to C#. All right. So this is a little brief history of Java. And I don't want to read a lick of it to you. I do want to say something to you, though, and that is this. Now, I'm going to quickly go out to a website, and so I'm going to go out to java.sun.com. That literally, right now, literally is what I am going to key in. That right there, it should be plenty big that everybody can see it. java.sun.com. So I'm just going to literally grab all this, and I'm going to go to a web browser. And in that web browser, I'm going to paste that in. java.sun.com. You can see it pushes me off to an Oracle site, which is fine. But to me, that's the easiest one to remember. The reason I'm showing you this is this right here on your screen. This is kind of the, well, how do I put this? This is the explanation. This is the help system. This is everything you probably will need to know regarding Java, is to go out to java.sun.com. And I'm sure they have something there too about the history of Java out there. So you can see Java is roughly 25 years old. And James Gosling, who was one of the people working on Java when it was in its beginning phases, had an oak tree outside of his office, and that's how the language first got its name. It was originally called Oak. However, from what I understand at least, when they tried to get that language and that name, there already was a language out there called Oak. Now, what happened next is basically it's up for debate rather. A lot of people say that Gosling and his contemporaries liked to sit and drink coffee, and it was during one of their coffee clutches that they came up with Java, which is another word for coffee. I don't know how true that is. If we look on the bottom bullet here, it says Java is cross-platform. And what that means is that you should be able to run a Java program on virtually any kind of computer. Already mentioned, there's two different types of applications. Most of the work we do in here will be applications. You can also run Java applets. The difference is an application is a standalone program, an applet must run under a browser. So, what is a computer program made of? Here you can see some of the components. I'm not going to read any of these to you. When we get into, I think, the next chapter, you'll see the Java keywords. Operators are things that you've used in the past. Plus, minus, multiply, divide, etc. Punctuation, what you're going to learn is virtually every line of executable Java code must end with a semicolon. Programmer-defined names are typically referred to as identifiers. That's what you use to name your parts of the program. Syntax we've already talked about. It's the rules of the language. Now, here's our first example of looking at a full-fledged Java program. Okay? Now, when you type this stuff in, although you may or may not have line numbers, depending on the editor you're using, line numbers are put there for your convenience. They're not part of the program. Java is a truly object-oriented programming language. What that means is when you use Java, you must use classes. Notice how this line says public class payroll. When you've got public in class, whatever follows next, like payroll here, that's what you must save the file as. Even the caseness must be the same. So if this had been a payroll with a big P, but I saved it with a little p, I'd have an error when I try to run the program. This is a really, really simple program. Java is a block-structured language, so all of your components go between opening and closing curly braces. And somewhere in every Java application, somewhere, you must have a method that's called main. Main is referred to as the program driver. In the first several chapters that we go through in this program, we'll put all of our code into main, as we've got right here. All right. Later on, we'll see how you write your own methods that are called by main or called by other methods. So you'll notice that the class, public class payroll, it's everything inside of the curly braces. Then you'll notice the public static void main string bracket args also has their own set of curly braces. Now, a couple things about this. The first thing it says there is public. Okay, well, if there's public, does that mean there's also private? The answer is yes. What we will talk about later on in much depth and breadth of coverage are public, private, and protected. For now, to say something is public, it's kind of like a public figure. So something that's public is accessible to everything and everyone. Class, so public is a keyword, class is a keyword, and this is a case-sensitive language. So class means that I'm going to create a class. I can only have, in each file like this that I create, in each file, like a payroll.java, there can be as many classes as I want, but only one class can be public. And that public class, again, the name of that must be the name of my file. Then I've got my opening curly brace. Then inside of here, okay, this right here is called a method. Main is a method. And the whole thing, public static void main parenthesis string bracket args parenthesis, is known as a method header. This says that the main method is also public, so it's accessible and available to all. It's static. Now, I'm going to give you a quick definition, but right now that's probably not going to mean much to you. And that is, static means there's only one of them. Look at it that way for right now. Okay. Void means that this main method does not return anything, so there cannot be a return statement in here because we're saying that it is void of a return. Main is the name of the method. So as in here, public is a keyword, class is a keyword, but payroll isn't. Here, public is a keyword, static is a keyword, void is a keyword, main is not a keyword. All right, but it's every Java program, every Java application always looks for a main method because that's where it begins program execution, regardless of where you put that main method. So this method named main, it is possible for us to bring in a bunch of arguments that are of type string, and each argument goes into its own location, and this bracket here means it's an array of strings called args. If that doesn't make sense to you right now, please don't let it throw you. All right, it should hopefully become more apparent as we go on in the course. Okay. All right, Then in lines 5 and 6, we're declaring and we are initializing three different variables. Line 5, we are creating a variable or declaring a variable called hours. We're saying it's of type int, which means it can only hold whole numbers, and we're initializing the variable with a value 40. Now, most people would read that line as int hours equal 40, okay, which is very natural. What the computer actually sees is take 40 and assign it to the variable hours, okay? Then on line 6, and the author is showing a shortcut here that I actually don't like. I wouldn't have done what the author did right here. I don't know if it's going to let me change this. Whoops, change this or not. So let's see. Yeah, this might be read-only right now at least, so I have to go in there and change it. But I want you to write, instead of what the author shows right there, okay? So the author is showing this. Double gross pay, comma, pay rate equal 25.0. I don't want you to write things like that. I want you to write it like this. I want yours to look like this. Double gross pay, double pay rate equals 25.0. In other words, I want each variable declared on its own line. Not only that, we saw in the earlier example where we said int hours. So earlier we came in here and we said int hours equal 10. So this is both declaring a variable, which is what this is doing, and initializing a variable, which is what this is doing. Here we're declaring a variable, but we're not initializing it. Here we're both declaring a variable and initializing it. So in lines 5 and 6, we declare three different variables. Line 7 is blank. And now we're saying that take the hours, which is 40, multiply it by the pay rate, which is 25, which gives us 1,000. Take that 1,000 and assign that to gross pay. And the system.out.println should literally print on the screen, your gross pay is $, and then we add to that, that's what the plus sign is here, gross pay, which we just figured out was 1,000. So this should say your gross pay is $1,000. All right. Now again, that may not totally make a lot of sense, and that is okay. All right. Remember, this is the first chapter. So what is a program made of? Well, you've already seen some of these. The keywords, I already mentioned most of them to you. Again, Java is a case-sensitive language. Keywords are virtually, if not always in lowercase. I can't think of one that is ever not in lowercase. So keywords can have a special meaning to Java, so you can only use them in that way. I already mentioned that semicolons are typically used to end a Java statement. All right, we'll see exceptions to that as we go on. Part of learning Java is learning where and how to properly use punctuation. It says there are differences between lines and statements when you discuss code. All right, it says this is one Java statement written using 2 lines. Okay, so you could put it in 2 lines like that. And even though this is 2 lines, it still is a single program statement. Data in a Java program is stored in memory. We already talked about main memory before. Variable names are used to represent a location or an address in main memory. Variables are created by the programmer. Okay, we already went over this. Variables, the author says here, are simply a name given to represent a place in memory. Well, my definition isn't much different from that. My definition of a variable is it's a named memory location whose value may vary. Hence the name variable. All right, in most programming languages, what happens in most programming languages are either compiled or they're interpreted, or they're both compiled and interpreted. Now, my students have heard this quick little interlude that I'm about to give you before, and you may or may not, those of you listening to this tape. That is, imagine that I'm at a Java conference, okay? And while I'm at the conference, I get let's say I'm speaking at the conference. All right, now I get done, and one of the people in the crowd who seemed very enthusiastic about what I was speaking about comes over and wants to introduce themselves to me and have a conversation. The problem is the person who wants to introduce themselves and have a conversation only speaks French, and I can only speak English, or maybe I speak other languages, but not French. So when the person comes over, they bring a friend of theirs who speaks both French and English. Okay? Well, if the person is speaking French very quickly, and let's say that the person who's going to be my translator, my interpreter, whatever you want to call it, let's say they even have a French to English and English to French dictionary. All right? So the person is speaking a mile a minute and trying to give me all the French that they can. And every time they say something where the translator does not know the English equivalent, or maybe doesn't even know what the word is, period, they write it down. They let the person keep talking, but they write it down. When they're all done, before they can translate to me and let me know what the person said, they've got to go look in their French to English dictionary to find out what exactly something means. When you do that, when you let the person keep talking until they're done, but you highlight all of their errors or things you don't understand, that's compiling. On the other hand, if that person is talking to me, and let's just assume that every time they say a word that the translator doesn't understand, they say stop, 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 whatever it is in French, stop, 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 and the person stops. They pull out their English to French dictionary and they find out exactly what that word is, but they're translating on the fly as the person's talking, they're translating. And every time there's a word that comes up that they don't understand, the person talking in French must stop. That's an interpreter. Now, for computers, most computer programs that are both compiled and interpreted interpret first and then they compile. Java's a little different. Java compiles first, and it's something that's done in the guise of what's known as the Java virtual machine. And after it compiles, so for instance, that program that we saw here before, this one, if we can compile that correctly, if there's no syntax or other kinds of errors in here, it will create a file called payroll.class, not .java, .class. And that file will be the compiled file. Then after that, basically the Java virtual machine, which is also called the JVM, will take that file and interpret it. And that'll be the running program. So the code that you write for a program is known as source code. You use a text editor to create your Java source code. Every Java file that you create is saved with a .java extension. And the compiler, as it says, is a program that transfers source code into some kind of an executable form. So the source code is the input. Any syntax errors during compilation that are discovered must be fixed. Again, mistakes in language. Okay. And the compiler creates another file that holds the translated instructions. That's that .class file. Most compilers translate source code into executable files containing machine code. In Java, again, it's done a little bit differently. These bytecode classes that get created by Java have a .class extension. The JVM, as it says, executes instructions as they're read. Again, it's typically referred to as interpreted. Java is often referred to as an interpreted language. I don't like that because to me, it's compiled, then it's interpreted, and that's what it means. So here's your program development process. You sit down with your editor and you code your source file rather. When you get done with that, you run it through the Java compiler. If there are any mistakes, you've got to go fix those and run it again, fix those and run it again. But ideally, sooner or later, you won't have any errors, so you'll have a bytecode file. That bytecode file will be read and executed by the Java virtual machine. Java is known as a portable programming language. As it says there, it means that a program may be written on one type of computer and then run on another totally different type of computer with little or no modification. Java virtual machines exist on virtually any kind of language platform. So if you were in this program and wanted to write your Java programs on a Mac, there's no reason technically you wouldn't be able to do so. As mentioned here in the second bullet, Java provides a Java virtual machine for each platform, so programmers don't have to recompile their code for different platforms. Now here are some of the different editions of the JDK. The JDK is known as the Java Development Kit. It's the software you use to write Java programs. And you'll notice when you look in here, there are different editions of this JDK. There's the Standard Edition, provides essential tools for developing applications and applets. There's the Enterprise Edition, provides tools for creating large business applications that deploy on servers. And there's the Micro Edition, which is a smaller, optimized runtime environment. Well, to my knowledge, the one that we'll be using is the Standard Edition. Could I be wrong? Sure, I could. When you actually go to compile a Java program, this is one way of doing it. You can type in Java C. The C in there stands for compile. So that's invoking the Java compiler. And then your name of your file .java. So for instance, if I wanted to try to compile that program.java file that we saw before, I'd put in the command at the very bottom of the screen here. Java C space payroll.java, where the P in payroll would have to be in uppercase. All right. Then, when you run the Java program, all right, so you've compiled, but when you're running the, interpreting it, whatever you want to call, that's the compile. Notice how it differs. Java C payroll.java. When you run it, it's just Java payroll. So no C on the end, and no .java, no .class, no anything. As mentioned here, this command runs the Java interpreter, the JVM, and executes the program as long as there weren't any errors in it. All right, now I'm going to have to talk with Mr. Goodmestead and find out. I'm used to teaching Java from using an IDE, and in particular, using the Eclipse IDE, or Integrated Development Environment. There are other IDEs that can be used as well. The IDE, as mentioned there, typically consists of a text editor, a compiler, a debugger, and other things. Okay? So the program is compiled and executed with a single click of a button, or by selecting an item or whatever. Here is an example of an IDE. In fact, this is NetBeans, which is another IDE. What you have here would look very similar to what you'd see if you were using a package like Eclipse. Okay, so here's your source code window. Here's kind of your file or project explorer window that's got the name of all your stuff. Here's got some more information about the stuff that's here. And typically, you've got this created, and if you want to run the program, you typically just click run or like the arrow that's here. Okay? All right. So they give you here a 9-step program process. The first step says clearly define what the program is to do. Now the interesting thing is there are 9 steps, but in an ideal world, you don't actually key anything into the computer until step 5 of 9. What you get out of doing it that way, so what you get out of actually waiting and putting the stuff into the computer later on, is step 1, you are clearly defining what the program is to do. So in other words, you're saying you understand it and you don't need a computer to be able to understand it. Next, you visualize the program running on the computer, which might mean something as simple as you draw it on a piece of paper what you want this to look like. Then you use design tools to create a program model. You check that model for logic errors. And if you say, I don't know what a logic error is, we're going to be talking about that. Then in step 5 of 9, you enter the code and you compile it. Step 6, remember, as we talked about much earlier in the chapter, most of the time when you create programs like this, there will be errors. So you correct any errors, and then you might do 5, 6, 5, 6, 5, 6 many times. You should also, when the program does eventually run correctly, come up with a set of test data and then run the program with the test data. If you find any other errors, you go back to step 5 again. You do 5, 6, 7, and 8. Because in step 9, as it says, you're validating the results of the program. All right, one thing I mentioned earlier is Java is known as an object-oriented programming language. What that means is everything that you do in Java must be done using classes and objects. All right? If you use another language, for example, I'm trying to think of a good one here, JavaScript. JavaScript is not object-oriented, it's object-based. What the difference is since JavaScript is object-based, what that means is you can write full-fledged object-oriented programs in JavaScript, but you don't have to. Languages are either non-object-oriented, like the C programming language has no objects in it, or they're object-based, like JavaScript, which means it has object-oriented capability, which you can choose to use or not use. And there's object-oriented, which means that virtually everything you do in here has to be done using objects. Now, what they talk about in here is kind of the older way, more of the C way of doing things, with procedures. All right? And I don't want to read this to you. There's an example. Notice data in the program tends to be global to the entire program. What that means is it's a good thing because there's less work for you to do as a programmer, but it's a bad thing because if program data is global, that means it can be essentially changed by any part of the program, which typically isn't a good thing. So with object-oriented programming, it's much more, it's modeling. So for instance, let's suppose that somebody was to come in and, in fact, let's look at the example. I know the Rams moved, but before they moved, there were architects that came in and showed the plan for a new St. Louis football stadium. Well, before they were to build that stadium, they wouldn't just go and start digging a hole or digging all over the place, in land that they bought. Instead, they would draw models first. All right? And that's what object-oriented programming is. You are modeling things in the real world. Now, back in the day, I remember this. I can't tell you how old I was, but I remember when reports were coming out how doctors were using mice and lab rats and injecting them with all sorts of things to test for cancer and all sorts of other things. And some of that is still done. But PETA, was that People for the Ethical Treatment of Animals, and other groups said that this wasn't fair. It was being very inhumane. So what some developers did was they would come in and write computer systems which would in essence they would model a digestive system. But now you wouldn't have to be killing lab rats. You could just be running code instead. So what does this have to do with anything? Well, object-oriented programming, which is also called OOP, you create objects. Objects hold the data, also known as attributes, and the methods, also known as behaviors, that operate or manipulate that data. I don't know if this is a good picture or a bad picture. So an object contains data, also known as attributes, and methods, also known as behaviors. And those data and those attributes can also interact with code outside of the object itself. Plus, you can have several types of objects that you create. You can have several copies or several versions of the same object, or you can have several objects. Much like if you were going to be building a neighborhood, and you were a home builder, you might have several house plans. Each one of those house plans, from each one, you could be creating house objects. All right? Those plans or blueprints are typically known as a class, and the actual houses that you create would be known as house objects. Object-oriented programming also deals with data hiding. And if you say, well, I don't know what that is, actually we all do. All right? I was thinking about this. When I leave for work in the morning and I take my car and I put it into reverse and I start to back up, I don't know. I'm not an electronic guy. I don't know what happens inside of my car to make that happen. I don't care what happens. I do care that when I put it in reverse, I don't go forward. All right? So the actual act of what happens inside of my vehicle when I put the car into reverse is hidden from me. And as it says there, it protects the attributes from accidental corruption by outside objects. If that still confuses you, think about it like this. If I come in here and here's my calculator, and I type in 329 and I hit the square root key, I have absolutely no idea how the system came up with that number, because the way that it did that, once I hit the square root key, that was hidden or encapsulated from me. I don't have to know how it's done. I just have to know that I have to type in a number and what key I have to hit. That's all I care about. And if for some reason tomorrow somebody came up with a brand new way of doing square roots that was faster and better, that could be technically implemented in the inside of this calculator. But as long as I typed in my number and hit square root, as long as my answer was the same, it wouldn't matter to me. All right? What you see in front of you right here, this whole thing, this is my calculator. That's my interface. That's what you let the world see. The code that actually makes this right here, 329, hitting the square root key, the code that actually went and made that square root calculation take place, that's the implementation. So the interface is what you show others. The implementation is what you hide from others. And that's what they're talking about here. We're hiding details about how something works. Object-oriented programming encourages usability and reusability. All right, so, and if that confuses you, think about it this way. Let's suppose that I get contracted by enterprise rental car. And they want me to write some kind of a new system for them because they're thinking that when people come in and want to grab a car, all right, not for people who do it online, but people who come in and just want to get a car then and there, it's taking too long. So I create some kind of a system for them that cuts the process way down. Now, Holiday Inn, the hotel chain, hears about that and says, well, you know what? You created this rental application, and by just tweaking it a little bit, yeah, yours is done for cars, but we could probably do it, and we could set it up also so when people want to get a room, all right, that's reusability. And as mentioned, their reuse of code promotes the rapid development of large software projects. I already told you about the attributes. They're also, attributes. Notice what they say. If I had a clock would have a second, a minute, and an hour data attributes. All right. Methods are also called behaviors. So I might want to be able to set the time or get the time or whatever. Most methods are public. Some methods are private. We'll get into all this in later classes. But in a nutshell, and what I'm saying here is a generalization, but in a nutshell, what object-oriented programming is all about is it's taking public methods and using them to manipulate private data attributes. All right, again, that's very much a generalization, but it usually holds true. So when we talked before, a class is a blueprint that you create objects from. So I could create a person class as an example. And I could say that every person would have a height, a weight, and let's say I made both those int height, int weight. I could give the person an eye color, a hair color, a gender, that type of thing. All right. And I could say that for each one of those, I might be able to set the height, get the height, set the weight, get the weight, set the eye color, get the eye color, set the hair color, get the hair color, set the gender, get the gender, etc. All right. So I could create all that stuff and make it a person class. From that person class, on an as needed or as wanted desired basis, I could create person objects. When you create what's called an instance of a class, that instance is an object. In fact, the act of instancing a class is known as instantiation. So every object is an instance of a class. A program, as it says, boils down to a collection of objects that interact with each other on an as-needed basis to accomplish some kind of goal. You're going to see this very shortly. In a much later chapter, we'll talk about inheritance. As it says, it's the ability of one class to extend the capabilities of another. And they say, consider a car. A car is a type of vehicle. So I could sit there and type in something like this. This isn't a great example, but it's the one I'm going to use. So let's say that I came in here. I'm going to get rid of all this. Make this smaller. Cut it down about in half. So let's say that I came in here and I created a class that was called vehicle. Well, underneath that class, I could have a class called car. I could have a class called truck. I could have a class called motorcycle. I could have a class that's called bicycle. And I could have a class, I don't know. I'll just leave it at that. How's that? So, car would be a child of vehicles. So would truck, so would motorcycle, so would bicycle. But then I could come down here and I could say, well, what kind of cars can I have? As an example, let's just do it. We'll do it based off of the car manufacturer. So let's say that I had here a Hyundai, which is what I have. And I could have a Buick. and I could have a Ford, etc. You get the idea. What we're starting to create here is what's typically referred to as an object-oriented inheritance hierarchy. There's my top level, also known as level 0. There's level 1. There's level 2. So level 0, level 1, level 2, etc. And you'll see more and more of this as we go on in this class. That's the way it's going to look when we use something that's called the Unified Modeling Language. So, the chapter ends talking a little bit about software engineering. And they mention that that's the process of crafting computer software. Software engineers, here's some of the tasks they perform. And guess what? In this class, you're going to do every one of those. You'll design programs from which you'll write your programs, from which you'll test your programs. When there are mistakes, you'll debug the programs. While you're writing the programs, you should be documenting them. When you're testing and debugging, you may have to modify your program. And what if I gave you a program to do X, whatever X was? Then for your next program, I wanted you to do X, but then I wanted you to add Y to it. That would be modifying and also maintaining your program. All right, that's pretty much it. So the first chapter was meant to give you an introduction to the Java programming language. When we come back and go through chapter 2, chapter 2 is on Java fundamentals. So I'll be back with that lecture shortly.